Okay. Hello everyone. So recently I was reading some function analysis, and there is this book by uh, Folland. It's written very nicely. So in mathematics there is a very important theorem called Riesz representation theorem. So I just thought that it's a nice idea to present this whole thing in a very systematic manner, building up from the scratch. So the first thing we need to know for the foundational part is that the notion of radon measure. So, before going to the definition of radon measure, so let me recall what is the meaning of uh, giving a topology on a set and putting a measure on subsets of X. So basically, let's recall what is topology and what is measure on some set X. So from the set theoretic perspective, so what is topology on a set X? So set X, you take a set X, and then you choose some subsets of X. And there are some rules, there are some particular rules for choosing such subsets. So for a topology, so what are the rules? So the rules are, we have to take the empty set has to be there, the whole set has to be there. And then if you take some collection of sets, let's say the collection is denoted by AI, where I belongs to I varies over some indexing set, arbitrary indexing set, then their arbitrary union has to be there. And if there is some finite collection of sets AI, then the intersection has to be there. Right. So this is the basic definition of topology. So there is a set X, and so this kind of collection of subsets uh, is known as, so this collection of subset is basically is a subset of the power set, right? So this collection can be thought of as a subset of the power set. So basically what it means is that we're choosing some particular subset of the set X following some particular rule. And what are the rules? You have to choose the empty set, you have to choose the whole set, and if you choose some finite number of sets, you also have to choose their intersection. And if you choose some arbitrary collection of sets, then you also have to take their union. So now, given a set X, there are various ways to define a topology on X. So that is topology from a purely set theoretical perspective, without any intuition or motivation for that matter. It's just I'm just saying what is topology purely from a set theoretic point of view. And then comes the notion of a measure. So what is measure? So here also you have to first you have to choose some particular collection of subsets following some rules. Again, similarly as topology. Now here what are the rules? So the rules are like empty set has to be there. The next rule is that if you take a particular subset A, you also have to take a complement. This is a bit different from the topology, right? In topology, there is no constraint like if you choose A, you have to choose a complement. But to define a measurable space, what we call a measurable space, you have to choose a particular collection which follows this particular rule that if you choose A, you also have to choose a complement. So the first rule is that empty set has to be there. If you choose A, then you also have to choose a complement. And the other thing is that if you choose, if you take a countable collection of sets, let's say AI, where I varies over some countable set, possibly infinite, then you also have to take their union. You also have to take their union. So this collection may not be this collection this collection may not be finite. So I varies over some indexing set I, where I is some countable set. Now this is some motivation. This can be motivated from real life probability scenarios. So maybe many of you already know about probability theory, at least have some basic knowledge on probability theory. So this can be motivated by notions of probability theory. So what is the motivation? The motivation is that the empty set signifies that no event has happened basically. So in probability we talk about events, and the empty set signified that nothing has happened really. So what does the second condition means? If you choose A, you also have to choose A complement. That means if you want to know what is the probability of happening, what is the probability of the occurrence of the event A, you also want to know what is the probability that A will not happen. So that is the idea, that is the motivation behind this rule. That if you want to measure the set A, you also want to measure the set A complement. And similarly, what is the intuition behind taking the countable unions? So what does it mean? So if you know the probability of occurrence of every event AI, you also want to know what is the probability that at least one of them will happen. And this notion of at least one will happen is captured by this countability. So that is the motivation behind defining a measurable space. So there is a set X, and then you choose this particular collection of subsets following some rules. What are the rules? You have to take the empty set. This is the first rule. The second rule is that if you take a set A, you also have to take its complement. If you take some countable collection of sets, let's say AI, where I varies over some countable indexing set, then their countable union also has to be there. So such a collection of subsets. So if you choose a particular collection of subsets of X following these rules, and let's denote this collection by some sigma, let's say, then this X sigma is called a measurable space, right? It's a measurable space. And then you want to define a measure on this measurable space. So measurable literally means that it's something which you can measure, which is to say that you want to define, you want to attach a number to this particular subsets which belongs to this collection sigma. Again, this sigma is obviously a subset of the power set of X. Okay, so now what is measure? So to each element of sigma, that means the collection of subsets that we have chosen, for each member of that collection, we want to attach a number, or more precisely a positive, or let's say non-negative real number, to each subset in that collection, following some rules. Now, what are the rules? Now, your intuition says that the probability of nothing happens, that should be zero. So that means mu of phi should be zero. That is the first. And then if you have a disjoint collection of uh, subsets AI, so this symbol means disjointing, and that should split up into disjoint sums, right? So that is our intuition behind defining probability. I mean, that's how we do in probability, right? I mean, probability of occurrence of at least one of them is equal to the sum of their individual probabilities, provided uh, they are kind of what is that called? I think that is called mutually exclusive. If I'm not wrong, the terminology is called mutually exclusive, I think. So basically, the probability of the occurrence of their intersections is basically zero. So then what will happen is that the probability of occurrence of at least one of them is equal to the sum of their individual probability. So these are taken as these two things are taken as a definition for defining the measure. That empty set should be assigned the number zero, and the number attached to the disjoint union is equal to the sum of their individual numbers. Now, any function which satisfies these two conditions is called a measure. Is a measure on sigma. So basically, I have attached a particular number to each member of the collection sigma, following these rules, that empty should be assigned 0, and the second rule, mu of disjoint union is equal to sum of their individuals. And this x sigma mu, so this triple denotes that I have a set x, and then I have chosen some particular subsets of x following these rules. Then we get a measurable space, and then to each member of sigma I attach a particular number. So basically I get a measure. So that's how we get a measure on subsets of, and by subsets I mean some particular subset. You cannot, it's not necessary that you have to take every possible subset of x. First, you have to define a measurable collection. By a measurable collection, I mean a collection which follows that particular rule. The rule I, the rule, this rule has to be followed. So this rule. So you may come up with some rule, I may come up with some different rule, and then we will end up at different measurable space. So for different people, this sigma could be different. There are various ways to define a measurable collection on X, and then there are various ways to define, to attach numbers on those subsets. So this is some basic recollection of what is topology and what is measured on a set X. And then there is a special kind of measure which is known as probability measure. So a probability measure is a measure which satisfies this condition, that satisfies the following condition. The condition is that the mu of the whole set should give the value 1. The mu of the whole set, that is the, so in probabilistic terms you may think of it like the probability of the occurrence of the event x is 100%, because since x is the whole set itself, that means the probability of the occurrence of the event x is 100%. So let me give you an example of probability measure, very basic example. So that you have done in probability at the high school level, everyone has done this. This basic example of coin toss, or tossing an unbiased coin, or rolling an unbiased die. So let's take a finite set. Suppose I take this set 1, 2, 3, and then my sigma is the whole power set. So basically I'm taking every possible subset of x, and then I'm defining a measure. I will define a measure on each subset of x by the following rule. So basically I attach 1/3 to each number. So basically mu of I equal to 1/3 for all. So I weight every number by 1/3. So then you can check that this is a probability measure. So basically I'm saying that suppose there is a 3-facet die and each face is numbered as 1, 2, 3, and that is unbiased. So that means probability of occurrence of any side is 1/3. So that model is captured by this measure. So if I say what is mu of the set containing 1, 2, so that will be 1/3 plus 1/3 equal to 2/3. Because mu of 1, 2 is just mu of 1 plus mu of 2 by the second rule for measure. We call the second rule, which says that mu of the disjoint union is sum of the individual numbers. That is what we are using here. That way it defines a probability measure on the whole power set. But for infinite sets, these things get very tricky actually. So sometimes it may not be possible to define a probability measure on the full power set. For example, you can take the real number. I think you can take this as an exercise. It's an interesting exercise, I guess. If you take real number, then can you define a probability measure on the whole power set of the real number? So you want to attach a number to each subset of the real number in a way so that it becomes a probability measure. And I think that is not possible. I think that is a good exercise to verify yourself that it's not possible. For infinite set, it becomes tricky.